Welcome back, and we're going to be doing optimal control and a real demo of it using their rig here. What in fact we're going to be doing is system identification and control, it'll be kind of optimal control. Linear-quadratic regulator is the proper word for it. You've seen the rig before, and I'm going to do some theory first before I come back to this. We're using, of course, LabVIEW and the myRio. So you can fast forward to the actual demo if you like, or you can watch a little bit of the theory, which I think is kind of important to understand. So here we have it. So some keywords we're going to be using: spectral factorization, that's important. Diophantine equations, that's an old word from the Greek, special kind of equation, but it's in polynomials. LQR, which stands for linear-quadratic regulator, in particular the tracking problem, or the set point can be varying. And we're looking at this kind of problem where we've got a system here which we represent as b over a. That's a ratio of two polynomials, or a transfer function. These are polynomials in the Z transform. A can be stable or unstable, B can be minimum phase or non-minimum phase. That's to say that the zeros of B can be inside or outside the unit circle. B must have a minimum of a one-step delay for physical realizability, because all systems have a minimum of that. But there can be any order you like, really. But in this case it's our motor, so the question arises, how do we actually identify the motor? How do we know what B and A is in real life? We'll come to that. And once we know B and A, we can calculate G and H, which are controller. That's the numerator and denominator polynomials of a controller. And we put negative feedback around it and operate it in real time. So the LQR problem has been around since the late 1950s, as far as I know, and it minimizes in discrete time the sum of the squares out of the output of the system, y, plus rho is the Greek letter rho, it's not p there, that's a rho, times ui squared, that's the control signal. Notice we only need one, this is called a weighting. We need only one weighting term. You could put weighting on both, but as you increase one, you effectively reduce the other in this scalar problem. So you could put the weighting on here, for example, and just one here. So it's like a normalization. So we only need change this weighting. We don't need control over this guy. Our system model is b over a, as I said before. Hope you can read that. That's z to the minus 1 over a, z to the minus 1. There's no noise in the system. It's a deterministic problem. This is a motor we're controlling. It's not some kind of system with lots of noisy disturbances or a chemical system process control. And the polynomials themselves, b is b0 plus b1 z to the minus 1 and so on up to b, or whatever order you like, n z to the minus 1, and a is that, one normalized to 1, the first term, plus a1 z to the minus 1 up to a n z to the minus n, can be unstable, open loop. In our case it's stable. You need at least one term here for physical realizability. You can't just have b0 on its own. b0 plus b1 plus whatever to model b. And as I said, a can be unstable in the theory anyway. B can be non-minimum phase, that's to say zero is outside the unit circle. And b must include any time delays. In our case it's just going to be 1. We don't really have any huge delays in this system, unlike in other applications. So what's the solution, or the algorithm that we run for the LQR? This isn't quite the LQR solution. It's very similar to the LQR solution. It's based, the true LQR solution is based on the Wiener-Hopf equations, which goes back to the times of Norbert Wiener in the 1930s, I think it was, and later books like Newton, Golding, Kaiser, and Euler especially, and then Kuchera did other solutions. So this is kind of based on their stuff, kind of loosely. I worked on this myself a long time ago with Professor Grimble, who's from Strathclyde University. So how do we do? Well, we need to identify our polynomials a and b. That's our transfer function. And we use recursive-least squares, or RLS. That's recursive-least squares. Now, you just have to look that up in the literature if you're not aware of it. It's a least squares procedure which runs step by step rather than a big batch of data, and it converges, hopefully, if the dynamics of A and B don't change with time, it converges to our system model. When we look at the practical side of it, we'll notice this is perhaps easier said than done as well. This itself has problems. Usually the system has to be persistently exciting, which means the input to the system needs to be rich in harmonics, and in textbooks this means usually putting in white noise. And although we can do that, we'll just use a square wave to achieve a similar goal. We need this thing called spectral factorization, which is step 2. We know the control weighting, so we've got A rho A star. Star means complex conjugate, so that means you multiply A z to the minus 1 times rho times A of z, and you get positive and negative terms in z. Plus b star equals d star, and it's the d term that we're actually after, this polynomial. And there's a number of ways to solve such a problem, and again you have to look it up if you're not familiar with this. Look for the spectral factorization problem. I'm going to use the Newton method, so I had to write the software for this as well. There's our A star polynomial, which is, if you like, the conjugate polynomial of A. If A's got all its roots within the unit circle, then A star's got all its roots outside the unit circle, or vice versa. Rho is our control weighting. Then we need to solve another problem, which is the Diophantine equation. So H and G are our solution polynomials for our controller. We have to solve this equation, AH plus BG equals D, and then apply our control. The solution to this can be done in a number of ways. It can be done using the what's called the extended Euclidean algorithm, which relates to integers as well. It goes way back to the times of Euclid. Or we can just invert a matrix, and here we're just going to invert a matrix. Again, a little bit tricky to the general case to do the code for this in LabVIEW, but nevertheless it can be done. And so what we're doing in real time is we're solving this, and we're going to be solving the Diophantine equation as well in real time. What we won't be doing in real time is the recursive-least squares. It's just a little bit too much. The other thing is, because the dynamics of the motor doesn't change with time, it's a fixed system, there's no need to keep continuously identifying the system on and over and over again. It's a waste. You only need to do that with systems change with time. But nevertheless, it is an adaptive system in that the controller adapts to the model that we estimate. So if it were to change with time, we could just run it again or identify a modified model. And then we apply this. This is just G over H is just an IIR filter transfer function G over H. So what we're dealing with is a motor, a DC motor. What we're going to do is we're going to put a bias on the input, and so it's running continuously, and we're going to put pulses in a square wave. That's going to be our input, and we're going to measure the velocity as the output. You may be wondering why we're measuring the velocity, not the position, because this is a position controller that we're dealing with. And the answer is, it's a bit too difficult to get RLS to work with velocity. Sorry, with position. Because to get from velocity to position is an integrator. Anything with an integrator in open loop means that for any DC you put into it, it just flies off to infinity, off to sort of saturation, and you get pretty rubbish results, really. So it's easier to identify the transfer function without the to the velocity, angular velocity, and not to position. So what we can do is add an extra integrator artificially in the model to get us to position, and that should give us the right transfer function, hopefully. So we're going to plot the Bode plot, and as I said earlier, we're going to use recursive-least squares. So the LQR problem is simply this: control input, and there's our system, our motor transfer function B over A. This is what you may come across in textbooks, the so-called Rmax model, which has got B and A and C upon A. We don't really need this. This is a stochastic disturbance, and this is what we use for solving what's called the LQG problem, the linear-quadratic Gaussian, as opposed to the linear-quadratic regulator problem. So the motor transfer function, Vn is voltage and omega out is in radians per second. Then it's well known, or we can prove this very easily, that the basic transfer function, ignoring inductance, is a first order transfer function like this: Km over 1 plus Stm, where Tm is the motor time constant, that's determined by the inertia and the resistance of the armature, and any coefficient of viscous damping is in there as well. Km is just like a gain term. Again, we don't know what these are. We have to identify them. We could, of course, do this in the analog domain and find out what that is and that is using various methods, but we're not going to do that. The actual transfer function we've got, however, is an integrated form of that, because we want position and not velocity. Velocity is just first order transfer function. Position's got an extra k over s term. So that becomes a second order transfer function that we're trying to identify. And in reality, we've got more than that. We've got a structural resonance term, which this is our second order poles complex conjugate with a damping factor. I think it turns out about 0.5 or something like that. Omega n squared over s squared plus 2 zeta omega ns plus omega n squared. And this is the rest of the transfer function we just talked about. So it becomes 1, 2, 3, fourth order we need. And no zeros to worry about, that we're concerned about anyway. We will need to, although we're using a fourth order, we can actually estimate it with a third order to give us some speed, and then add the extra integrator to make it fourth order. Maybe one way to do it. So let's now talk about the demonstration. So back to the demonstration. Here's my LabVIEW front panel, and it's rather big. It's split in three. The first part is where we're doing the identification. There's an LED, there's a light here that gathers, that tells you when data is being gathered. The second part here is just displaying some of the numerator and denominator polynomials that the recursive-least squares algorithm estimates. And the third window over here is our real-time window. It then goes on to implement it in real time. It does it all at once. So all I need to do is press the button, and it should go off and work out estimate the system and work out the controller. My control weighting, I'd make it anything I like really. Let's just make it something like, put it up here, 20. So that's my row term that I talked about earlier. There it is. That's the control weighting. I'm going to also, in the real-time system, I'm going to put a square wave in. I'm going to frequency 2 Hz, so it's just going back and forward aimlessly. This is my spectral factorization part. So this is where I should see the results of my spectral factor. It'll converge. You'll see it flicking round until it converges. And this is my Diophantine equation solutions. We look at the code. This does the initial. The instrumentation is done on the FPGA. That you've seen that before in other videos. That's just to measure velocity and position if we need position later. So that just gathers the data and it stores it in an array, and then it fires it. It takes out any DC, and it fires up it into the recursive-least squares algorithm, which is just a sub here, which in itself is quite complicated. Here's the recursive-least squares algorithm over here. I haven't got time to go into recursive-least squares. You can look that up, but that took quite a while to write. I've got here I can add an extra integrator. I explained this earlier, to make my polynomial goes up one order, then my A polynomial. So because I'm actually measuring from velocity, I want position. So once I've done my measuring, I then add in an extra integrator into the A polynomial and just continue. And then I do a board plot just to see, well, just the magnitude to see if it makes any sense. And then go on to the real-time part. It goes straight on to the real-time. There's the spectral factorization bit, which is this uses the Newton method of spectral factorization, which does quadratic conversions, which is quite fast. And each one of these things is can be rather complicated. And the Diophantine equation is a sub as well. Here it is. And this is done with matrix inversion. Only tricky bit here is really just setting up the matrix itself, because it requires a lot of shifting of, well, polynomials, which is like vectors or arrays, shifting them and putting them into the matrix. And when we've got it, we just then do a matrix inversion. As I say, I'm not suggesting this is the best way to do it, but for small order problems it's probably the easiest. You can use extended Euclidean algorithms, another way to do it, rather than inverting matrices. And there are other ways to invert matrices rather than straight inversions of matrices. There are other neat ways to do it. We can also store the results and plot them, and that's about it. So let's run it. Now what am I doing here in terms of the running? I'm going to be putting in a DC value, which is velocity, and then superimposing a square wave on top of it. So you'll hear the motor sort of running speed, and it sort of goes faster and slower, a little bit. Let's run it. There it is, gathering data. There's the motor turning. You hear it fast, slow there. And if we go back to here, you'll see that it's there's the board plot. So just to make sure this does make some kind of sense, this should have a slope. This is our first integrator. That's got a slope of about 20 dB per decade, if we look at it roughly. It's come down that amount, and 20 dB, about 20 dB in 1 decade. Now here, from 60 to 20, at this point here, has gone to minus 40, from minus 20 to minus 40 dB per decade. This is a second roll off. So first roll off minus 20 dB per decade, and then minus 40 dB per decade. And then what you're seeing down here is like a structural resonance. That's our structural resonance, which we can measure as off the cursor. It's about here somewhere, 2.13 kilohertz, and these are the actual parameters that the thing is estimated. So this is the recursive-least squares results. And what I've done is I've picked a numerator order of 5, just I've made it a little bit bigger than it needs to be. Sorry, a numerator order of 3 and a denominator order of 5. Beg your pardon. Numerator order, so NB is 3, NE is 5. I've added an extra integrator. These are my numerator coefficients. They're steady state now because the recursive-least squares run very quickly, and then there's the roots, and there's the denominator ones. So that's my B and my A. Now let's go over to the real thing, and I put a square wave in, and it's actually running, and it feels pretty strong actually. So let's do some recordings. to see how good it is. Oh, before we do that, let's just look at the convergence of the spectral factor. Well, I say it's converged there anyway, but if I change the control weighting, then it has to change the spectral factor. So let's change it. You see that, see it's changing all the values. That's it. I mean, it's pretty fast convergence, but it's just like the one to about the 5th decimal point it's fiddling around with to get it right. I mean, we don't really need that level of accuracy, but that's what it's doing. And likewise for the Diophantine equation, it's having to change in them as well. So if I move it again, you see the parameters there are all changing. It's the spectral factor on the top, and that's the two polynomials G and H we talked about. So let's make it 20, the control weighting, and do a recording. Then I'm going to stop it. So this recording, let's say 1, 2, 3, 4, and then stop it. And then we go, there's the response of the tacho, and the red is the set point, the white is the output. There's a tiny bit of overshoot, and there's a little bit of offset as well, and, surprisingly. Well, although there is an integrator in the loop, it's a mechanical integrator. It's not an electrical integrator, it's just a natural integrator because we're measuring position. At least we're measuring position here at this point. We never measured position when we did the identification, because that's, although we can measure position, identification is very hard to do when there's an integrator in the loop. So we measured just from velocity and then put an extra integrator in artificially. And that's the frequency response of the controller, Diophantine, and it just goes up like this at very small slope, and then it sort of seems to shoot up like that. I'm not quite sure. I suppose it's some kind of phase advance, but there it is. It seems to be working. We can run it again. Let's change the weighting. Let's put it down to somewhere low. And I'll just, I didn't of course need to stop it, but I'm just going to run it again. That's the motor turning, doing identification. And you see it's a very similar model to what we had last time. Slight difference, but very minor. And I'm going to just turn off the, oh no, it's still on record, sorry. So I have to run it again. So run it the third time. Again, very little change. And now I'll do a recording. Ignore that, whatever that is. Stop it. There we go. There's a little bit more overshoot this time with the lower weighting. Okay, and now that can be improved on. Of course, we can put another integrator in if we need to. We can perhaps look at that. Change the weighting, but we don't have control over bandwidth. It's just that's how it is naturally. I'm going to run it one more time and just put a manual set point in. Again, it's doing another. Again, we needn't necessarily identify it every time. I could skip straight to the actual thing itself. So let's turn off the square wave and just put a manual input in. And so there's our manual input. And so this is, remember, an optimal controller. It's not PID, it's not lag lead or anything. And this sort of thing was discovered in around about the 1970s. Basic idea slightly before then by Euler and some of the mathematics earlier. It's very strong here. Oh no, it's not actually that strong, this one. Not as strong as my other one I had. But it's not bad really. Could do with a little bit more gain. But extremely well damped. No problems with instability. So every time I run it, it finds a different solution. Thank you. Okay, so now I've run it, I don't know, fourth time is it? And I've put the weighting up to 50 this time, so it's a large weighting on the control signal. I've got no input at all. I'll put it in a minute. Now it's a little bit better. It's very hard to actually resist it when it moves. Oops. Trying to move it with this thumb. You need two hands to do it. Let's do another recording. Record. Oh, I'll put this time it'll record me with the frequency changing. As you can see, it's recorded the change in the frequency, and then there it is with the really nice kind of output, isn't it? That it gives you. Finally, you may be interested. If you don't put the integrator in, if you haven't got a proper model, then you've got a model just from this point of view of speed. Let's have a look and see what happens when you do that. Of course, we'll then we won't get our integrator here. We won't get a -20, -40. We'll just have a flat, or something nearly flat, and then it'll go down because it'll be first order plus the thing. Let's run it again. There we go. So that's the transfer function of the motor from speed to input rather than from velocity. And you see the structural resonance much more pronounced there in the motor. And that's the DC gain. It's still working, but not as well because we haven't modelled the extra integrator. Let's see what it does. Let's record it for a few seconds. 2, 3, 4, and there you go. So we've got much more overshoot because our mathematical model isn't right. It hasn't taken effect of the integrator within the motor itself. We've just kind of ignored it and modelled just from velocity instead. Whereas we need to measure from position. Okay, there's a lot to this topic, and of course we can do this in state space, which is another topic I'll be getting to, and hopefully give you a demonstration of that as well. But in the meantime, I hope you enjoyed this. This is quite unique. I don't think I've seen any real-time polynomial LQR implementations on servos. Certainly not like this anyway, where you can actually change the values. There's a great many MATLAB simulations out there, of course, if you want to check. Although again, not so much on polynomials, but using Kalman's methods of LQR. So when you're doing this, you have a choice whether to use polynomial methods or whether to use, which is transfer functions, or use state space approaches. Thank you very much. Bye-bye.